requested, we have numbers, I think, 3 and 7 from the Math of Light quiz. And then we also have numbers 9 and 10 from the practice problems. So we're going to start with number 3 on the quiz. So I expect that you will be looking at that as I'm reading it, and then we're going to work through it together. Meaning I'm going to work through it and talk it out, and you are going to pay attention. So the distance from the Earth to the Sun is 1.496 times 10 to the 11th meters. So distance is, and there's a reason why we're using D instead of the displacement. So here is the distance, and that is in meters. A solar flare occurs on the sun's surface Wednesday morning at 10:24. We'll use that information later. At what time, that's our unknown, and on what day will the electromagnetic radiation from the flare reach the Earth? Okay, so remember that light travels at a constant 3 times 10 to the 8th meters per second. Okay, so even if we did use this equation, okay, if the velocity of light is constant, which it is, it's 3 times 10 to the 8th meters per second, no matter what, the acceleration is 0, which leaves us with a glorified D equals RT equation. Okay, so having said that, now we can continue with the problem here. Let me get rid of all of it. Okay, so we're looking for the time, and it says to use the fact that the velocity of light is 3.0 times 10 to the 8th meters per second. So we have D equals RT, and we're solving for T. So 1.496 times 10 to the 11th equals 3.0 times 10 to the 8th times T. Now we'll divide 1.496 times 10 to the 11th over 3.0 times 10 to the 8th, and that is going to give us the time in seconds. Okay, so once we do that division and we adhere to our 2 significant digits, we get that the time is 500 seconds, which is 5.0 times 10 to the second. Okay, but that's not very helpful. 500 seconds isn't very helpful. Maybe converting that to minutes would make it more helpful. So we're going to use 500, but allow for the significance in that middle spot there, the first 0 from the left. So we're going to change 500 seconds to minutes. And there are 60 seconds in 1 minute. Okay, so when we do the division, 500 seconds divided by 60 is going to give us, rounding to these 2 significant digits here, 8.3 minutes. Okay, well, if the solar flare occurs Wednesday morning at 10:24 a.m., what we have to do is just add 8 minutes to 10:24, which is going to give you 10:32 a.m. on that same day. Okay? All right, moving on. Number 7. Okay, number 7 on the quiz Determine the frequency of electromagnetic energy that would have a wavelength of 1 mile. Okay, so we are looking for frequency, and frequency is found in that equation. Okay, so our wavelength is given in miles, but we need our wavelength in meters. So we know that we can convert 1.6 kilometers to meters. And that means when we multiply by 1,000, we're moving this decimal here 3 places to the right, which is going to give us same number of significant digits, okay, 1,600. 2 significant digits in 1.6, 2 significant digits in 1,600, okay? So that's the wavelength. Now we just need the frequency. The speed of light divided by the wavelength that is now in meters. Okay, and when you do that division, you're going to do 2 significant digits in your division, and you are going to get, out of scientific notation, 190,000 hertz. If you put it into scientific notation, it would be 1 times 10 to the 5th. Right? 1, 2, 3, 4, 5. Okay? So I don't know exactly what the problem was with that one, but doesn't matter. There you have it. Now we will move to the practice problem number 9. Okay, so now I expect that you will be opening your books. And we are on page 384. Okay, number 9 says the work function of gold is 5.31 electron volts. What is the lowest frequency of light that will result in electrons being liberated from the metal? Okay, so if the work function, is 5.31 electron volts, okay? That means that in order for the electrons to be freed from gold, the energy of light has to be 5.31 or a little bit more, okay? If it's less than that, not all of the electrons are going to be freed. But the energy of light has to be 5.31. So when we look at our equation here, okay, that E stands for the energy of light, which is equivalent to the 5.31, the energy of light needed to free the electrons from gold. Now, H is Planck's constant, but because we were given our work function in electron volts, we are going to use Planck's constant in terms of electron volts, which is this value right here. Then we can solve for the frequency, okay? That is the lowest frequency of light that will cause all of the electrons to be freed from the metal. So we are going to divide, and we have 3 significant digits in the numerator, and we have 3 significant digits in the denominator, which is going to give us a frequency of 1.28 times 10 to the 15th hertz. Okay, that answers the first part, number 9. Then it says, what is the wavelength of the light? Well, now that we know the frequency, we're going to use our frequency equation along with the velocity of light and solve for the wavelength in meters. So the frequency we just solved for equals the velocity of light over the wavelength. Okay, so we interchange the frequency and the wavelength, lambda. So we get that the wavelength is 3.0 times 10 to the 8th over the frequency we just solved for, and then we will get our wavelength in terms of meters. So 2 significant digits in the numerator. And when you do that division, you are going to get that the wavelength is 2.3 times 10 to the negative 7th meters. Okay? So remember, work function is the stubbornness with which a metal holds on to its electrons. And because of that, that's the same amount of energy that light has to have when it shines on that metal to make those electrons become freed from the metal. So work function is the stubbornness of the metal along with the energy that the light needs to free the electrons. Okay, last one, number 10, practice problems. Light of wavelength 211 nanometers. So we're going to write that down. The wavelength is 211 nanometers, shines on copper, which has a work function of 4.94. So I'm just going to abbreviate that. The work function is 4.94 electron volts. What is the maximum kinetic energy of the electrons that are emitted from the metal? Okay, so we need to find the frequency. Okay, so we need to find the frequency. In order to use it in that equation, okay? Remember that energy, E, is the amount of energy that light has to have on the metal, copper, in order to free the electrons. So we have to first find frequency in order to use frequency in our work function equation. All right, so we'll start here. The frequency is equal to the velocity of light over, and remember when we convert nanometers to meters, you're going to move the decimal 2 places to the left, and the power is then to the negative 7th. So 2.11 times 10 to the negative 7th. Okay, and we find the frequency then to be, I got to get my calculator. Hold on a minute, guys. So, and I know you're doing this along with me. Open up a fraction. 3 times 10 to the 8th over 2.11 times 10 to the negative 7th. And we have 2 significant digits in the numerator, 3 in the denominator, so we are going to abide by that and use 2. So 1.4 times 10 to the 15th. That is the frequency, okay, when our wavelength is 211 nanometers. Okay, now we can use that in our work function to solve for the energy that light needs to free the electrons. So because we were given the work function in electron volts, we are going to use Planck's constant version of electron volts. So times 10 to the negative 15th times the frequency that we just solved for. which will give us that the energy needed by light is, and I'm doing this on my calculator, 4.14 times 10 to the negative 15th times 1.4 times 10 to the 15th. And we get, now, 3 significant digits here, 2 here. So the energy needed is 5.8 electron volts. Okay? So 5.8 minus 4.94 is going to be the maximum kinetic energy of the electrons that are emitted from the metal. So we'll line that up. 5.8 minus 4.94, and our significance is right here, okay? And we get the 0.86. So the 6 is going to bump the 8 up to a 9. So we get 0.9 electron volts. There you go. That's number 10. Okay, guys. Hopefully that helped. See ya.